Continuing on with our circle properties and some theorems that go with it. We're looking at two different properties here that deal with the tangents in circles. So in the first one, so that's the one up at the top, we have a tangent and we also have a radius. Now, if you have the radius meeting the tangent point at the point of contact, so the point of contact is where the A is, it will always make a 90-degree angle with the tangent line. Okay, so that's by definition, that will always happen there. All right, so a radius will meet a tangent at the contact point to the circle at a 90-degree angle, no matter what. All right, in the second theorem that we have, I'm just going to put the circle center in here just so we can refer to it. What we have happening is the theorem states, if we look at our contact point here, let me call this A, and I'll make my other contact point here for my other tangent. So there's two different tangents here. We'll call that one B, and I'm going to call this point where the two tangents intersect each other, I'm going to call that point C. Now, what this theorem says is that the AC line segment, so from the external point C to point A, point of contact, that length will be actually equal to the other tangent length from that external point C to the point of contact. Okay, so there's a whole thing that we could draw with, and I'll just run through that quickly. It's not part of the theorem, but this is why the theorem works. I could draw my radius in here. That's going to meet at a 90-degree angle. Draw my other radius. This meets at 90-degree angle. This is a radius, and this is a radius, so they're equal to each other. If I join the center to here, I then have two right angle triangles. So triangle AOC is right angle, as is triangle BOC. Okay, those are both right angle triangles. They share the hypotenuse and they have a second side equal to each other. So by default, Pythagorean theorem, that third side would have to equal each other. So these two triangles are actually congruent to each other, and it means that those two side lengths, AC and BC, will be equivalent there. All right, so the definition I wrote is that if we have two tangents to a circle and they're drawn from that single point, so my point C is my common point or my single point, to the circle, so a tangent from point C to the circle, so I have my two different tangents, CA and CB. The length from the common point C to the point of contact A or contact B, those two lengths will be equal. So CA in this particular case is equal to CB. All right, so we're going to use these theorems now that we've learned to solve for some indicated angles, some indicated side lengths, and then a mishmash of different stuff. So looking at this first example, we're going to solve for angle AOB. So angle AOB is this angle in here, which is a central angle. Because we have O being the center of our circle, we know that that's the Star Trek symbol, so that central angle will be twice, so angle AOB will equal two times that 37 degrees, that inscribed angle there. So 2 times 37 would be 74 degrees, I believe, if I did that correctly. All right, solve for angle JKL. So JKL, I'm looking for this angle. So the letter in the middle is really where the angle is. The first letter is just telling us how we could trace out the angle. So from J to K to L, it's the angle in here. All right, now notice that JL is actually a diameter. That means that angle JKL is lying on that diameter, which means it's 90 degrees. All right. Okay, moving on to the next example, we're solving for angle PRQ. So P to R to Q would be this angle right here. Now I'm noticing PR is a diameter, which then means that the angle at Q is 90 degrees. So we could take 180, subtract the 90, subtract the 39, and we're going to get 51 degrees here for angle, I should do that in a different color, for angle R. So I took 180 degrees, we're subtracting the 90-degree angle, we're going to subtract the 39-degree angle, and that's going to give us 51 degrees there for that angle that we wanted. All right, moving along, solve for angle C to A to B. So that's this angle here. Now, again, I've got a diameter CA, which then means that the angle at B will be 90 degrees. And I'm also noticing that it's an isosceles triangle because I have those hash marks. So what that means then is if I could take my 180 degrees for the sum of the angles in the triangle, subtract the 90 degrees, that gives us 90 degrees. So the angle A plus the angle C have to add up to 90, but since it's isosceles, those are equal to each other. So 90 degrees divided by 2 would give you 45 degrees. Okay, so angle CAB is going to equal 45 degrees. Okay, so a couple different theorems that we're using there, the circle theorem and then isosceles triangle theorem. All right, part E, solve for angle CBD. So C to B to D would be this angle here. And I'm noticing that both angle A and angle B are subtended by the arc DC. Okay, so I could trace that out. So that angle will be equivalent to the angle at B. So that means that the angle we are looking for is simply, let me get the correct tool out here, simply going to be equal to 43 degrees. They're equivalent to each other. So that's that bow tie symbol there. All right, looking at the next one, solve for angle WXV. So W to X to V would be this angle in here. That angle is inscribed on arc WZ. Okay, I can trace that out like this, but I also know that this is inscribed on arc WZ, so that angle that I'm looking for will be equivalent to the 18 degrees. So this one, that's equal to 18 degrees. And then if I want VZY, just change my color here, V to Z to Y, I want this one. It's inscribed on this arc, so tracing this out, it will equal this one because it's also on the same arc, so that one's equal to 25 degrees. So hopefully you can see what's going on there. So that's 25 degrees. All right, moving on. And in example 2 here, we're solving for the measure indicated by the question mark. So I'm looking at this diagram. Now, in any of these diagrams, if it looks like a tangent, it is a tangent. Okay, we're going to assume that's true in this particular case. If I had that question mark symbol and I didn't know it was a tangent, what I would have to figure out here is actually if it's a tangent. Now, assuming it is a tangent, this is a 90-degree angle here. So I've got a nice little right angle triangle where I'm trying to solve for hypotenuse and I know my two other sides. So question mark squared would equal 12 squared plus 16 squared based on Pythagorean theorem. So we can work that out. So 12 squared plus 16 squared, that's going to give me 400. So square root that, 400, square root that, and the question mark will equal 20. Okay, and they're side lengths, so we don't have to worry about the negative answer. All right, so try the next one. See if you can figure that out, and then I'll work through it. Okay, we have a radius and a tangent, so that is a 90-degree angle triangle. This hypotenuse would be 2.5 collectively, 2.5 here. Now, our radius, so we're trying to solve for this side length, but this side, we actually know, even though it's not written, it's a radius, which will be equal to this 1.5. So we can use the Pythagorean theorem, but knowing the hypotenuse is 2.5, we kind of work backwards for that. So 2.5 squared, the hypotenuse squared, will equal 1.5 squared plus the question mark squared. Okay, and we could use an x or something instead if you would prefer. But we're going to figure that out. 2.5 squared minus the 1.5 squared to move things around. That gives me the question mark is equal to 4. So 4 is equal to the question mark squared. And then square root that, we get 2. So the question mark is equal to 2 units. All right, I don't like using the question mark, so I'm going to make a letter X for this one. Again, you're going to try and figure this out. We have a radius meeting a tangent. That's a 90-degree angle. I need that side length. I think I can use my Pythagorean theorem again. And then we can solve for that diameter. Okay, so if you check your work for part C, you should have gotten that diameter is about exactly 7.5 units long. If I wanted the radius, I could just cut that in half to get that value. All right, D is a little bit trickier here because I don't actually have any side lengths figured out. And what I want is actually an angle in here. So we got to work with some angle stuff. Again, we're going to assume that we have a tangent line here. So the tangent meets the radius, that's a 90-degree angle in there. So I do have a right angle triangle where I know my 90 degrees, I'm trying to get the question mark. I'm wondering if I could get that central angle value somehow. Now, if I take a look at what I have a radius right here, and I have another radius right here, which makes this isosceles. Okay, so those two side lengths are equal because they're both radii. This 63 degrees then would also be 63 here, which is part of that 90-degree angle. So in this little triangle inside here, I could figure out the central angle by taking 180 degrees and minusing those two 63-degree angles. Let's see if I can actually make a 3 instead of a 2, 63. So we've got two groups of 63 that we're taking off of that, and that will give us our central angle here. And when we calculate that, we get 54 degrees out of that. Now I can use my big triangle. I'm going to outline that in green. We know the central angle here is my 54 degrees. We know it has a 90 degrees. So this angle now up here will be 180 minus the 90-degree angle minus the 54-degree angle. And I apologize, this is all kind of smushed together and out of order. But hopefully that's making sense for you. So that question mark angle is 36 degrees. That was the one we needed to find. All right, take a look at E, see if you can figure that out, as well as F, and then you can turn the video back on and see how you did. All right, so for E, what I have is I have a radius meeting a tangent, so that's 90 degrees and 90 degrees here. I know that angles in a quadrilateral, so this whole polygon here is a four-sided figure, so it's a quadrilateral, they have to add up to 360 degrees. So if I have 360, I'm going to take off the 117 degrees in the center, and I'm going to take off the two 90-degree angles, and that will give us the angle in question here. So we'll have 63 degrees as our answer. Okay, so that angle is 63 degrees. For part F, I have a common point B. I have two tangents coming out of here, and our theorem says that these have to equal each other. So this will just be a straight on 12.3 units, and in fact our units are centimeters. Okay, now take a look at the next example. The last example, determine the perimeter of the polygon. These are very closely related to the very last example that we did. You're going to need to find some more information to be able to add up the side lengths for perimeter. In part A, we have a triangle as our polygon. We want the perimeter of that triangle. And in part B, we have a quadrilateral. So see what you can come up with there, and then you can check your work. Okay, based on what we have, this little section here is 11.2. That means this section here is 11.2. If I take that 23.2 and minus the 11.2, I get 12. So this piece is 11.2. That means this piece here, let me use a different color, this section is going to be exactly 12. And because of our tangency things, this also now has to be 12. And let's pick a different color. This part here is 10.5. That has to equal this part, which also makes it 10.5. You're going to add all those values together to get your perimeter for that triangle. So when I calculated my perimeter there, I got 67.4 units. All right, try part B, see how you do with that one, and then go ahead and find its perimeter. Okay, and based on the theorems that we have, I got 78.8 units as my perimeter for that quadrilateral in part B.